Cybersecurity concerns are ever evolving. OT cybersecurity is even more complex, and it's so much more than just software and hardware. How do you stay on top of it all? Aaron Crow has over 25 years experience with cybersecurity. 15 of those years focused on operational technology across multiple industries, and he wants to help you. Welcome to the Protect OT Cybersecurity Podcast, brought to you by Industrial Defender. Now here's your host, Aaron Crow.
Hey, thank you for joining me today, Matt. Why don't you introduce yourself, tell us a little about you and what it is that you do, and what have you been working on?
All right. Well, thanks, Aaron. My name is Matt Scott, and I'm a OT security professional. Been working in the OT space for about 3 decades now. Started in process control in the process industries, and then worked into machine control, and now I work in the space of mass transit and using industrial control systems for control and monitoring of high volume mass transit systems, light rail, streetcars, things like that. What I've really been working on these days is how to secure kind of legacy OT systems, particularly in the transit space, because we focus a lot on the rail industry. We have a lot of legacy systems because of the regulation and standards that are set by the industry. We can't really be on the cutting edge. So we have a lot of older legacy technology that we employ, but we have to employ it across a larger and larger geographical space, which puts us into more and more networking, more communications, and that puts us with more exposure to vulnerabilities. So how do we take those legacy technologies and make them secure kind of in this new space of geographical dispersion and a lot of dependence and exposure on communication networks?
Yeah, it's the age-old story. I have these conversations a lot of time. I'm fortunate to be able to have conversations with really smart people like you, and the story is the same. The industry can change, but it doesn't matter if it's critical infrastructure. It doesn't matter power generation. It's all the same. We have legacy equipment. We can't just go replace it. It's dispersed throughout the land. There's limited people that have the skill set. I have to be able to secure and remediate. And patching is not the answer. Replacing the hardware is not the answer. Like, I can't just go do that in mass across these large, environments that are spread out everywhere. That doesn't mean I can't do nothing. I just have to find a different way. So OT, I'm excited to have conversations like this where people are working to find other ways to secure and make these processes available and secure and reliable without saying, hey, well, you're not patched and there's a vulnerability and focusing on probably the wrong things in the OT space, because that's not probably going to help. Patching a system isn't going to necessarily make your process more secure and more available.
Right. Yeah, I think what happens today is you get a lot of, kind of market-generated solutions. People want to sell you OT security systems that do asset identification and inventory. They do vulnerability, checks, and then suggest different upgrades or patches that you need to employ. But when you're dealing with that legacy element, they're not going to find those patches, right? There aren't any available, and a lot of the vulnerabilities are really kind of architecturally based. So what you really need to do is you got to go kind of back to basics, and you've got to build into your design the ability to mitigate tomorrow's exploitations. And so that really that means that you've got to look very closely at your functional use cases, but then look at what I call the abuse cases. How can your functionality be abused or be exploited? And it doesn't always start with, well, they could inject some code here, or they could capture a particular packet of data. What you have to look at is what the intent of someone doing the exploitation is. And usually what we talk about in our industry is they want to turn us off, and they want to get on the news. They want to be in the media, right?
Sure.
So you have to look at that and say, what would make us stop running? What would make an event that would end up in the media? And then look at what that means for an abuse case, right? And a lot of those things, what they really focus on is you end up at the PLC layer. You end up in that that transitional space between the cyber and the physical, right? They want to be able to do something in the cyber domain that will result in a physical event, a physical demonstration, right? And so that's really where I've been focusing is you've got to look at, yes, as part of a well-grounded defense in depth of OT, you want to be able to deploy these products. You want to be able to look at a legacy system and extract what your inventory is. What are all the assets you have? What are the versions you're running? What are the hardware platforms you're running? Are there known exploits? You want to run lots of intrusion detection, lots of perimeter protection, right? But that's not where, if you really look, that's not where historically the attacks on OT that result in a physical event, that's not where they come from. They come from, our good old friend Stuxnet, right? They come from somebody who's supposed to be in the plant, who brings in some malicious code and puts it in through the engineering workstation, right? So they didn't break into your remote access. They didn't violate your network protocols, nothing like that. They put it directly into the processor. Then, you have things like Triton that come along where now they've learned how to manipulate the processors at the firmware level. And so how do you protect against malicious firmware? And that, in my research, that's like a big hole that exists right now, particularly amongst the PLC vendors. No PLC vendor has the ability to say what firmware is running in your processor right now. You can have a record of what you last downloaded into it, but there is no tool that's available to query the processor and say, what firmware are you running, and can I get a hash from it and compare that to the OEM and see if it's malicious or not. So that means that you've got to have a process. You've got to have an approach that enables you to, from the beginning, make sure that you don't have any violations of that, that PLC core layer, the firmware, the software, the hardware that you're going to run it on, and the functionalities that you're trying to accomplish. So that's where you really need, you have to think security by design. So security by design, everybody says, oh yeah, that sounds very logical, that's easy to do, right? We just make things secure from the beginning. Well, how do you make things secure from the beginning? That requires an entire life cycle approach. You've got to have what I call a security development life cycle. So we're all familiar with the software development life cycle and kind of how that starts with, you develop your requirements, and then you put together a design that meets those requirements, and then you write your code, and then you test it, and then you maintain it. But what's missing from that is the security element. How many times when you're writing requirements for an application, for an OT application, are you really sitting down and saying, how can this system be exploited? And then once you've determined those requirements, how often are you really saying, oh, okay, these requirements require this particular hardware version from this OEM? How often are you saying, well, is there a better way to do the functionality that will allow me to use a different, more secure hardware platform instead of the legacy one that we've been using or the standard one that we've been using? So what I've developed is kind of this security development life cycle, and what that really breaks down into is pretty typical elements. The first is requirements, but before you begin your requirements, the first thing you need to do is you've got to have not just process knowledge, but you've got to have security expertise. So you want to have the same kind of process that goes through to develop what are the requirements for this application going to be to, move water from point A to point B, or to, create this chemical mixture. You've got to have the same thing with security. And so somebody can look at it and say, if I were a malicious actor and I wanted to upset that process in a way to create an event, how might I do that? What are the things I could do? Could I send a erroneous set point outside of range, typical operating range, like we saw in the Oldsmar exploitation? So you've got to have that there, because when you're doing your analysis, you need to be able to create what I call the abuse cases, or the security use cases. So you can say, here's this functional use case. This is the subroutine we're going to write for chemical addition. Now, what happens when somebody tries to exploit that? and then we can say, okay, what are the types of functionalities we need to have to prevent that exploitation? So like take the Oldsmar kind of a simplistic situation where essentially somebody was able to put in a very, very high chemical addition set point, and there were no checks in the code. It just simply said, hey, we've got a valve in there that would allow between 0 and 10,000 parts per million, so why not send it 10,000 parts per million as a set point? Well, you would say, hey, do we ever add that? Would that ever become a possibility? And then you recognize that what you need to have is you've got to have some input validation. You've got to have some checking to say, based on our current operating conditions and our typical operating conditions and today's conditions, what is the range that we want to allow? Is that going to be a static range, or is that going to be a dynamic range? And then that becomes a use case or an abuse case that you need to mitigate against. And then you can write code that can do that, and you can write code once that can do that for any kind of input, and then you can instantiate that throughout your code and protect the situation where you're bringing in external values, either operator entered or passed from another system. So you do all that up front in your design, and then once you've got your design set, now you're ready to go implement your system. But you kind of have to now have to take this defensive approach, and that's what I call these defensive programming techniques for OT systems, and they really kind of fall into three main arenas. The first is establishing a secure code environment. The second is to define your rule sets, and then the third is to verify the initial code. And what we mean by the initial code is the code that is exercising your rule sets. So we'll get into that here in a second. So establishing your code environment, that's one of those things that people don't think about a lot is, okay, I got to write some code. My customer or my plant itself is using this particular version of a controller, and so let's go write the code in it. Well, what you really need to do is you've got to take a look at that and say, how secure is that platform? The hardware itself, we all know from going on the CISA sites, right? We can search by that platform and we can find, dozens of vulnerabilities, right? So we want to look at that, and we want to make sure that the hardware we're going to deploy on is as secure as possible. So we might find that there's different versions that you need to supersede with to get rid of vulnerabilities that the OEM has come out with. Or you can look at it and say, the way that this processor is going to execute a particular function, we can't eliminate that. Our functional application needs this. So now we're going to have to do it through code. We're going to have to write some code mitigations to protect us against this known vulnerability that has been exploited. And that really is super important. I can't overemphasize that. About 15 years ago, I dropped the ball on that piece, and I was working on a system and just didn't pay attention to, hey, what are the known vulnerabilities, and not even security vulnerabilities, but what we call weaknesses, right? And so there was this processor that we had selected for the project, and it had a weakness in it where when you ran, if I recall correctly, I think it was a divide function. But when you ran a divide function, as the value of the remainder grew, there was an error that was introduced. And so we were using that function, of course, in some code to do a flow totalizer, and what it ended up doing was it ended up over totalizing the amount of flow, and the customer was using that value to bill their customers for delivered product, and then it was a huge overbilling. So had I known that weakness was in there, we would have either chosen a different version of the hardware, or we would have written some software mitigations for it. So it's very important to get that code environment nailed down.
So how do you do that? Obviously, when you're doing this in greenfield and you're stepping in and you're designing a new system, and you're able to kind of look at those things and be able to look at the requirements of what this function, what the device needs to be able to do, right? But what about the environments where they have those systems already there, and they're not just ripping out all the PLCs that are already there? How do you secure that? Because obviously you can't just go replace 10,000 devices in the field, at least not overnight. But that doesn't mean you shouldn't do anything, right?
Right. So that's where in this process of evaluating and establishing your code environment, you accept that your environment has vulnerabilities, that it has weaknesses, but you've identified what they are. And now you move into that next stage, which is, defining your rule sets. So you start to publish standards within your facility or your plant or on your project, and you say, hey, we have to use this hardware. We have to use this level of firmware, whatever it is. And it's got some known vulnerabilities, some known weaknesses in it. So therefore, we have to put into our code, before we execute our actual functional application, we have to write some code that is going to prevent this weakness from being exploited. So kind of like that Oldsmar example, we're going to make sure that nobody can ever write a out of range value into our set point, so that we would end up with a overdosing situation. So it's the same thing. If you've got a hardware platform or a firmware version that has a vulnerability or has a weakness in it, you write code and you say, okay, like let's say that remainder issue with the divide block. You're going to write code that's going to compare the result of that calculation to the last known good value, and then you're going to take action on that, right? You're either going to say, hey, throw that value out and hold the last one, or you're going to determine what the offset needs to be. So you're going to do that through code, and you're going to write that as a rule. And then what you're going to do is, depending on what platform you're using, say you're using Siemens PLC platform, you're going to write a function block, right? And you're going to write a standard function block that says, anytime you're using this math function, or anytime you're doing an input from an operator terminal, you're going to employ this function block, and you're going to use the logic that's in it to mitigate this weakness. And then if you do that correctly, and you establish that as a function block, or like in the Rockwell automation world, AOI, add-on instruction, you create that. Now you can protect that. You can protect that so that code can never be changed. And then you can ensure that all of your developers, all of your programmers are instantiating that code throughout their programs. And now your vulnerability is mitigated. You've defined this rule set. You've said, hey, every time we have an input that's coming from some source, you have to employ this input validation function block. And now we have the ability to mitigate that. So we can use vulnerable hardware or firmware because we've got a software mitigation. So it's sort of like what you're doing is, first you're going through and you're doing your requirements, and in your requirements you identify vulnerabilities, and of course the security and the process people get together and say, is there a different way we can fulfill that process function to just eliminate this vulnerability? Right. Then if that's not the case, it's like, no, there's only one way to do this. Then we move on and we say, okay, now let's evaluate our hardware, our software, and our firmware. Are there ways that we can mitigate any exploitations there? And vulnerabilities there? Can we upgrade the firmware? Can we change to a different hardware platform? Can we use a different software version? And then anything that's left from that becomes the rule sets that we say. We say, okay, now we've got to mitigate all those things through software. Sure. And we set up this library of function blocks that mitigates that, and then we instantiate that through the code. And then what we can do with that is, as you're living out the life cycle in your facility, you have the ability, like on the Siemens platform, you have the ability to do logic compares. So you can periodically go back and compare to make sure that that logic has not changed, that those function blocks are still being used, and that they're unchanged, right? And that they're still locked. So that's kind of how you step through this. And if you do that, then essentially what you've got is a secure system that, whether your perimeter defenses, your intrusion, mitigations, your remote access, somebody brings a USB stick on site, if all those things somehow fail, and you've got you've got malicious actors that are into your system, you have at the bottom level of your defense in depth, you've got protections and mitigations against that. And that's that. And one of the things that's really handy about this is you don't have to dream up these abuse cases, and you don't have to dream up these mitigations. People like MITRE with their ICS attack matrix, they've cataloged many of those, right? What the abuse cases are and what the recommended mitigations are. And then what's really cool is you have this group from Europe called the PLC Security Project, who developed the PLC Top 20, and they've already set out standards with includes even pseudocode that says, hey, these are the top mitigations for the kind of exploits that occur at the PLC layer, and here's how you should mitigate them. And then you can use that to develop your function blocks, your models in your platform. And those are the tools that are really right there. They're free, free for everyone to access, and they really are helpful once you put them into this overall security development lifecycle.
Yeah, and it's really changing the thought process around what I'm trying to do. And to your point in the beginning, there's a lot of tools out there that are talking asset inventory and vulnerability and all that kind of stuff. And all those things are good to do. But I think for whatever reason, there's been this message in the OT space over the last 5 years or so that's enough. Like, it's like, 10 years ago when it was firewalls. Well, I've got a firewall, I'm good. Now I've got these asset discovery tools, I'm good. And I think you're talking about it, I've been talking about it as well in a different way, but it's not enough. Like, there is no silver bullet. I can't just, security's not one thing that I grab a product off the shelf and I'm done. The other piece to this that I love about the way that you're talking about it, right, is today, you design this Siemens PLC, right? And it's the best one on the market. It has no known, vulnerabilities in the wild, et cetera, until it does. 6 months down the road, there's a vulnerability, because all of these devices, they didn't start out with vulnerabilities. They were learned down the road, right? So all of the things that you put out, even if they're the brand new things right off the shelf, best in class, all that kind of stuff, that doesn't mean they're not going to have vulnerabilities tomorrow. So working on your code and making it reliable and secure, and it goes to that security in depth piece. And let's say you can't patch it, I can then adjust my code to knowing about this vulnerability. I can adjust my code with that in mind to fix it that way. So it just gives you multiple ways to remediate and mitigate these issues. And it's not always patch. It's not always replace the hardware. There's this code thing is really the crux of all of the things that we're doing in OT. And it takes people to be able to focus and look at that. And unfortunately, there's a lot of organizations that don't have someone like you that are able to understand that and put the process people and the security people together to look at that code and do that, right? And unfortunately, a lot of the vendors don't even have that skill set in-house.
Yeah, and what's really ironic is, like at the early part of my career, and, I'm dating myself, but was in the late 80s, and we still had at that time a lot of, unreliable systems. We had unreliable sensors. We had analog I/O. Our PLCs didn't do floating point. If they did, our end devices didn't. You're working on a paper machine and you have to display the speed on a message display. You had to convert to BCD, right? So in order to filter out unreliable data from sensors and failed instrumentation, in order to drive kind of ancient I/O devices, you had to do a lot of work at the code level to check and validate, right? Because otherwise, you would send out bad data or you would use bad data, and so that was just part and parcel to our work. But as things became more reliable, as we started to replace, analog I/O with IP devices, and we could just send floating point values natively, everything became very casual in the code space. And now what you have is you've got this security environment that comes along, and it really resurrects all these old, methods, because that's what, it's the same thing, right? Yeah. Somebody's trying to exploit your system. What they're trying to do is crash your system the same way some, unreliable sensor did back in the 80s. So now you employ those same those same checks, those same validations, and that that's what's interesting, is that people have kind of lost that well-disciplined code of the past. But if you bring that back and you use those techniques, you are the last line of defense, right? And you can mitigate these exploitations. You're not gonna always prevent them, right? And no product is ever going to prevent them. There's always going to be somebody that can exploit the next weakness, but you're going to be able to stop it from causing a physical event in the system. You're going to be able to send a notification to the people on, in the control room or wherever. So it's kind of like that's where this defensive programming came from. It was like, hey, let's go back to really well-disciplined code, and we're going to mitigate and we're going to prevent these cybersecurity events, but also at the same time, we're going to make our systems more resilient, because that's kind of, again, I know it sounds like we're really harping on it, but it's like that Oldsmar exploitation. And in fact, there's some new information that says it might not have been an exploitation. It might have just been an operator error. But it never would have happened if there was just kind of those fundamental elements of input validation, in the HMI, in the PLC. Hey, we would never put in 10,000 parts per million. We would only put in, 800. So let's make sure that no signal can ever go through above that. And that's what we would have done in the past. We would have said, hey, we got this old analog level transmitter, and if it fails, it can send an out of range value. So we would do a range check, and then we would do a check against the last known good value, and make sure that there wasn't a rate of change event. So there's those kind of things are coming back into favor, and I think that's what's really important. And what's great today is we have all those tools. Back in the day, we had to just write those over and over and over again, but now we have the ability to encapsulate them into a function block or an AOI, and then we can just store them in a library, and we can make sure that all the developers use them. We have tools that can go through and scan the code and check for them, and if they're not there, we can make sure they get put in. So there's a lot of automation that's available today to make that easier, but it's still the same things that it's sort of the old Shakespeare, right? Past is prologue. So if we do those things and we adhere to the kind of the well-disciplined code ideas of the past, we can make our systems very resilient, and particularly to cybersecurity events.
Yeah, absolutely. It's just like I see all the kids now wearing, styles from the 80s and 90s, and it's a blast from the past. It's the same stuff that we used to have back in the day. So, again, dating myself, but you're so right. Like in cybersecurity, I've been doing this longer than it was called cybersecurity. I've been doing it longer than it was called OT. Like it was not called those things, but I was still doing the same things. It just didn't have that title, right? I didn't really get the OT title until like 2010, but I've been doing this for longer than that, right? I've been doing this since, the late 90s at least. And the funny thing is that, like you said, though, it's all basic stuff. Like cybersecurity, it's just a particular threat vector, right? But most of the attacks or most of the things that happen that bring down an OT network or bring down a process control network, does it matter? And do I, as a plant manager, really care if it's China or if it's Bob that just put a set point in the wrong place? At the end of the day, all I care is my system available. Make sure that life is safe. Safety and availability is my most important thing. I don't necessarily care. You look at Colonial Pipeline. You look at all these different examples of OT things that have happened. Most of them haven't even been in the OT space. I worked in a power generation environment, and even in a nuclear facility, there was an incident on a crane that was completely air gapped, and the vendor brought in a malicious code on his USB stick and plugged it directly in the protected environment. Right? You can't just say, well, I'm air gapped or secure by obscurity. Right? That code is the final straw, and to your point, it gets back almost to the days of human performance. Like, I want to make sure that I put labels, and when you go into a certain place, am I on unit 1? Am I on unit 2? Am I in the right location? Making sure, double checking, three-way communication. Like, there's reasons we've done this from human performance. We should also be doing that in our code, because to your point, it's just because the valve will allow 10,000, if we don't ever want to allow more than 800, then we should set hard limits in there so that nobody can accidentally, even if I'm just Bob and I go in there and I'm new and I thought it said 800 and I actually put it to 1800. Like, I can very easily do that, and it was just a mistake. It wasn't a bad actor. It wasn't China. It wasn't Saudi Arabia. It wasn't anything, but it still had an impact on my OT environment, and that matters. And this code can help you to understand and reduce the probability as well as the impact if somebody makes a mistake, and you get alerts, all those kind of things, which is hugely beneficial. But it's really hard to do if you have gotten away from it in your organization. You've been lazy or sloppy, or even not even that, just not knowing that what you're doing is putting yourself at risk at that code level.
Right. Yeah, and it's it's interesting in some of the research that I've done, looking at you look at what is the source of vulnerabilities and exploits in industrial controls, in OT, and there's a whole sundry of them, right? But when you really drill down on it, you find out that almost 50% of them, 47% of the exploits and the vulnerabilities in OT are improper input validation. And another 8% is just poor code quality, right?
Right.
So together, those two are more than half of your vulnerabilities. So a really simple technique can mitigate over half of your vulnerabilities. And then you can drill down on the buffer overflows and the code injection and those kind of things that are more dependent upon exactly what you're deploying and what you're trying to accomplish. But that's why I really like that PLC top 20. That approach is just like, if you put those things into effect, you can mitigate the significant amount of the exploitations. So what's really kind of one of the things that when I talk about this, of course, right, today everyone goes, well, what about AI? Can AI help us here? And you have people, I know, I think there's Pantera is a company that says, hey, we've got an AI that can do some validation of your code and things like that. But really, I'm not a big believer that AI is going to solve our problems when it comes to code quality and defensive code and code that mitigates vulnerabilities. Because, one of the things is when it comes to ICS, operational technologies, PLCs, things like that, you're in a proprietary world, right? So you're not going to go find some large language model that's going to handle, your PLC S7 1200, right?
Right.
And then even if you've got legacy devices that are coded in, graphical language like ladder logic, you're not going to find a big database for that. So what you are going to find, though, I think, is that you can use, again, going back to this idea of defining these rule sets and creating these reproducible code models. You can use machine learning techniques to enhance those. So what you can do is you can say, okay, let's say we started with something simple like putting input validation to say the value for this input can never be outside this range. But you still have a vulnerability there because that range has to be big enough to cover any plausible situation in the plant, right?
Sure.
But what if now you're able to start recording over the last 30, 60, 90 days of what has been the operating range for that? Because maybe like if you're in a water treatment facility, it might be dependent upon the weather, the ambient temperature, the amount of solids in your water intake, those kind of things. Now you can look at that and you can start to employ those ML techniques and find what those patterns are, and you can change that range. You can make it dynamic, and you can say, okay, you know what? At this particular time, I know last week we were letting you put up to 800 parts per million, but this week you're only going to be putting 150 because anything outside of that doesn't correlate with the conditions that we have going on, and that would be considered an invalid signal. So I think there's the potential to use machine learning concepts, not so much AI concepts, but machine learning concepts, and enforce your rule sets in your code, your secure rule sets, to make them dynamic so that they can move to the conditions. And so I think there's a lot of potential there. And so as people, we all know in the OT world we're a couple decades behind everyone else. So as we start to pull ourselves forward, when you go through those life cycle upgrades and you change to a more powerful processor, or you increase the amount of memory available in your system, you can start to employ these things. You can take those code models you wrote just to mitigate, simple situations, like from the PLC top 20, and you can begin to enhance those, and you can make them much more powerful.
Yeah, that's the more that we can do that, and we are 20 years behind, right? But I've seen a vast difference in the last 5 to 10 years of, moving in the right direction, right? And heading and thinking about some of these things and putting security in the design and having a security person at the table and thinking about these things as I'm designing these systems. I've told this story a few times, but I remember designing a control or working on the team to do a control system upgrade project, designing the control system, and the vendor actually came to us with 2 options. There was the secure version, and they actually called it the insecure version. And that wasn't all that long ago, right? And so the fact that we've come so far, that same vendor would never, and no vendor that I know of would actually even market their product as insecure. Not saying that obviously the secure version is really secure, but the fact that things are at least moving in that direction, and people like you are looking at the code base, and we've got a lot of different ways that we can attack things. One of the biggest things I see in OT is that it's not necessarily that the technology is behind, it's that there's so much OT equipment out there, and we're just behind the 8 ball from a timing perspective. And there's so many companies that are, you look at a train system that has hundreds of thousands of miles of train and all of these equipment all over the their track and their rail system, or whatever the manufacturing that's global, and you look at it like that's a bigger problem, and transmission substations that are spread across the country. There's just so much of it, and they can't just go. It's a capital project. It's the people to do the work. It's the skill set to understand what needs to be done. So talk a little bit about how can you do this. Let's say you walk into a place, they're a big organization, they've got places all over the world, and they've done 0 of this, secure development on their code base. How do they get started? Like, what does that look like for somebody that's just beginning?
So I think it really comes back to that, those 3 components of the defensive programming. The first thing is, let's establish what your code base is. Now, your code environment may not be the same across every facility. It may not even be the same within a facility. If you're working in a manufacturing facility that may have 3 or 4 stages done across different departments, each one might have their own code environment. But you need to understand what that code environment is. You need to go out there and, say, okay, we're in this location, we're using this hardware platform. We need to vet that against the CISA now has these ICS dashboards. You can simply just put in the model number of your hardware, and it'll tell you what all the known vulnerabilities are, and then what the recommended mitigations are. And then you do the same thing with, what is the firmware that we're running there, and then what is the software we're running. And once you understand what that is, then you kind of look for the lowest common denominator, right? You say, okay, at one particular facility, we can't move off of this hardware, we can't move off of this firmware. Do we have a really good reason to be at our other facilities on a different version, or do we want to bring everybody to the same version? But even if we don't bring everyone to the same version, the way that we want to write our code is so that the code can go into any one of these versions and be secure, right? So we kind of break things down to that lowest level and make sure that we're, there might be a vulnerability that's not inherent in a newer version that's in one of your plants, but because you want to be able to control your code base and have standards, you write all your code, regardless of where it's going to get loaded, to make sure it mitigates the known vulnerabilities of the lowest version, right? And then you codify these rule sets and you publish them. You put them into your developer's manual, into your PLC coding standards, and you make sure that those are enforced by contractors, consultants, providers, OEMs, that kind of a thing. And then what you've got to have is you've got to have a mechanism to test that. So once you've said, hey, we've got all these different versions, but we're going to write everything to this level, and now we've published that. Now what you have to do is, just like you go out and you check your PLC batteries, right, on a preventive maintenance kind of cycle, you do the same thing. You go out and you pull the code out of a processor and you run it through the tool to make sure that those mitigations are inherent in it and that they've not been deviated from. So you kind of have to take this active approach on that. And then, the biggest thing that you run into is, even people who do that and are very well disciplined, they tend to sort of just make it static and say, okay, now we've got it set, we don't have to do anything about it. But as we all know, new vulnerabilities come out, new exploitations come out. So you need to be able to constantly be looking at, what do I need to do to enhance the defenses that I've got. And one of the biggest issues, like I said, that we've run into is firmware control. You can't query the processor and say what firmware's in there. So what you essentially have to do is, on a periodic basis, you've got to say, all right, hopefully we've got good records of what firmware was in that processor. Let's go get that firmware from the OEM. Let's check its hash, make sure it's legitimate, and let's reload it into that processor. And just to make sure that we don't have some unsigned firmware that was loaded in there. And then what we've got to do is, this is one of the really critical elements, is you want to manage the firmware vulnerabilities, because they're kind of the place today where your malicious actors are going, right?
Yeah.
Like in Triton, you saw that they were able to use certain elements of the firmware to enter the system, and then they learned from that, because the system went into a fail-safe shutdown. They learned from that and said, oh, we can start injecting our malicious code during the boot cycle, because we understand the firmware better. So you've got to be able to stay on top of that firmware. But as we've learned, you can't always count on the firmware being seamless. Okay, you've got an older processor, you put some newer firmware in it, and all of a sudden your code doesn't execute the same way. And so that's why, like I said, you've got to write everything down to that lowest level. Because when you break it down to the lowest level, it's a lot easier to check against a new firmware revision and say, is this code going to execute properly? Because if you start using embedded functions or higher level functions, sometimes they don't execute the same way on the new firmware, but the low level functions will. So that's another piece that you need to do, is you've got to have the security people work with the process people and say, is there a way that we can do this function differently? Can we do it at a lower level? And then that way we can write, again, it's like going back to the future, right? We're writing really low-level code again that we used to have to write a long time ago because we didn't have more powerful processors and a lot of memory. But the lower level the code is, the better, right? It's just like solving a complex mathematical function. You break it down into those lower level functions, and it's much more simple, and it's easier to validate because you validate each step. So I think that's really what you have to look at, is you've got to go out there and establish what your code environment is, and then you've got to put your sets in place, your rule sets, and then you've got to do a lot of validation. You've got to do a lot of testing on a recurring basis.
Yeah, and then when you do that, you're able to upgrade and go to the later versions, and you know that your code base is secure, and you can test that functionality. And moving forward, you're just going to become more and more secure as you're able to roll out. Because again, that's the thing I hear a lot, is I don't have the capital budget to go replace all the PLCs in my environment. I don't have a lot of them don't have firmware patches or OS. I can't update them anymore, right? They're at the best they can possibly be, and they're still vulnerable. What do I do, right? And so this gives you an option that you can secure your code base, you can secure your process automation, your business process, without having to just go replace everything in the world or buy all new equipment and all that comes entails, which by itself doesn't necessarily make you more secure.
Right.
Yeah.
I mean, going into an existing facility, like, as you say, if you don't have the ability to replace the hardware and things like that, putting in some function blocks that have already been tested and have been proven that mitigate vulnerabilities, inserting those into the code, and now that code that's running on a quote-unquote insecure platform is now secure.
Yeah, and I mean, I guarantee you there's a lot of OT environments, more than we want to probably admit, that, you know, they're running on code that has been hodgepodged and 15 different people's hands have been in there, never looking at it from a secure by design model, and they don't touch it because, you know, that maybe the person that started it out or really understood it is no longer with the company or whatever. So they're not even safe. Don't look at that thing. Don't breathe on it heavy. If you touch it wrong, it's going to fall over. So having somebody like you and in that mindset that can look at that and understand what it's trying to do and see where the gotchas are of, hey, if we do this differently, we can do the same thing, except it makes it better. Like it's taking really, you know, messy code that's been bolted on over you know, decades potentially, and cleaning it up and making it the least amount needed and more particular for what you're trying to do, right?
Yeah, definitely. I think that's, you know, that's like one of the things, like you mentioned, is over time, PLC code in particular kind of degrades, right? It ends up, it's no longer as modularized as it was originally was. You know, there's different approaches. You know, there's no standardization. There's different approaches being used throughout it, and that's again is that piece. If you back up and say, okay, you know, this idea of establishing your environment, setting rule sets, and then validating. If you back up and say, don't even take a security mindset for that. Just take a mindset of, let's evaluate our environment and let's set some rule sets, some standards that work across all our environments, and then let's make sure that we're adhering to them. That will clean up your code, right? And it obviously, absolutely, you know, like I said, you know, there's a component to vulnerabilities that comes from just bad code quality, right? We've all been through the scenario where a system goes down or an event occurs and people go, how could that happen? It's never happened before and we didn't change anything, right? And it's like, well, you didn't change anything. However, there was always this weakness that was inherent in the way that your code was written because you didn't write it very cleanly, and so it could always happen. It just never did, right? And so I think that again, yeah, that's the approach. Is I kind of look at it as, you know, because I have to sell things, right, to people who don't have a lot of money in the public arena, and so you want to talk to them about, you know, they'll say, oh, I'm not going to buy into that whole malicious actors and cybersecurity exploits and attacks, but I'm like, well, what about failures? What about hardware failures? What about, you know, loss of communication? You know, recently up here in the Pacific Northwest where I'm located, there was a water plant that was down for maintenance, and so they had filled their high reservoir before the plant went down for maintenance, and then they had some issue and they called in a contractor, and the contractor asked somebody on the site to reboot a server, and the way that their code was written for the reservoir is it did not hold the last value that was brought from the reservoir's level transmitter. So when they rebooted this server, it caused the reservoir to call for more water, and they ended up flooding the downtown of this little town and collapsing their reservoir. And so it's like, those are the kind of things that I try to talk to people about. I'm like, now, the same event could have occurred from a cybersecurity attack as well.
Right.
But, you know, this is much more likely if that's how you want to think about it. And so why aren't we putting these kind of controls in place just to make your system more resilient to failures and, you know, and operational upsets? So that's really, that's what I say this is all about. It's really about system resiliency. And
absolutely. Yeah, and the more that we can get that message out there, right, is too many vendors or whomever, the news, whatever, right, is talking cybersecurity and nation states and fire and brimstone and the sky's falling and, you know, China's coming after us. And I'm not saying none of that is true. But at the same time, the plant manager that's been running that location for 40 years, that's never happened to him. So put it into something. It's no different than when you turn on the news and you see somebody that their house was broken into or they were mugged or whatever happened. If it didn't happen to you or it wasn't in your neighborhood, it's like, yeah, but that's not me. That's never happened to me. Until your car gets broken into, until your dog gets stolen or you get held up by, you know, knife or whatever it is, then it becomes real. And that, to that guy, I guarantee you, he would look at that code differently now because he had an incident. Was it a cyber incident? He doesn't care. Like all that cyber does is add an additional attack vector. It means that somebody in China can potentially do this remotely. Or you have people outside the organization that are able to do it across a computer instead of having to physically walk up and turn a valve at a pump station to put the water in that dam. That's really the only difference that we're talking about. It all comes down to risk, though. And that risk is just that they overflowed that reservoir. It didn't matter how it happened, but it happened, right? And all that we're talking about here is cyber is just bringing a good spotlight on these probably things that, like you said, we used to do really well. We got out of habit from, and now we're circling back around and coming back to, hey, we need to focus on the basics and the foundations so that all of these things, we're reducing our risk, we're improving our resilience and our availability in these systems the way that they're supposed to be, and just putting in technology isn't necessarily always going to it'll fix some of the problems, but definitely not all of them. It is a bigger picture program that I've got to do, people, process, and technology, and that process piece is really important that we don't always focus on in this OT space, at least not in the last 5 to 10 years.
Yeah, definitely. I think if you look at technical debt of any OT, it's going to end up being in your PLC code, your processor code. You know, that's where your technical debt is, and that is a vulnerability, right?
Yeah.
And so, and that's the piece. Ironically, that's the piece that most people are afraid to go dig into. They're like, no. Why don't we just take care of the upfront piece? We'll put in some good perimeter defense. We'll have virus detection, all those kind of things, and then we'll be okay. It's like.
Right. Well, and part of it's just lack of understanding. And in my experience, it's when I don't understand something or it's working. OT's very much been, if it ain't broke, don't fix it. My dad worked in control system stuff for 40 years. All the way back, obviously, way back, starting in a long time ago, when everything was analog and everything was 4 to 20 milliamp and everything was serial, right? And as they grew and as they changed, that was always their motto, though. If it ain't broke, don't fix it. So they're not going to go from a Rockwell PLC to a Siemens because they already have Rockwell or they already have Siemens, whichever it is. It's not that Rockwell's necessarily the best, but that's what I've got. So that's what I'm trained on. That's how I know how to create the code and all the things I need to do. If I switch to something else, I'm going to have to learn that. Like, I'm going to have to train people on it, and all my people know how to do this. So I don't want to rock the boat. Let's just, how do I not touch that stuff? Like, to your point, add a firewall, give me virus protection. Like, what can I do to make you go away so I don't have to look at the underlying technical debt, like you said? I love that we're calling it that, because that's really what it is. We don't talk about that in OT, but that's what it is. It's technical debt that nobody's paying attention to.
Yeah, and it compounds, right? Like interest, because you've got, whenever you bring in another system to expand, or what do? You say, hey, grab the code that we've already got and put it in there, because we're just doing the same thing over again.
Copy and paste.
Yeah.
I just copied all that bad code everywhere in my environment, and I'm not even looking at it, because again, it works, and I have never had an incident. It's the analogy I always give. You can buy a brand new car and never change the oil, and I've driven it 200,000 miles and I've never had a problem until you do. Eventually, it's going to catch up with you, and that's kind of where we're at in OT with that technical debt. Is we've never had a problem that we know of until we will, right? Until it's, hopefully we find that and we start fixing them before they catch up with us, and not after the fact. Because unfortunately, in my experience, a lot of times it takes a bad incident. It takes the reservoir overflowing for people to really be comfortable or be forced to make a change and look at things because they just don't want to. And before that, it's too risky. They have to put their name on the line, and it's scary, and I get it. But we can't just do the Heisman anymore and say, don't touch my environment. Right.
Yep, exactly. Yeah, so it's really, it all comes back down to fundamentals, and that's always the piece that I guess gets left behind. I mean, we've all been through, cut our teeth on new processes and things, and how when you're doing code development, you get real caught up with, well, I'm trying to make this, this cascade loop function work here, and you just get caught up in that, and you forget about, the fundamentals, and then you run out of time, or you run out of budget or whatever, and so it's like,
Right.
just make it work,
Make it work. Yep. And then Bob comes behind you and makes something else work, and then Steve comes behind him, and Susie comes behind him, and it's just a cycle that and nobody goes behind them and says, "Is there a better way to do this?" Right? So awesome. So all that we said today, what's in the next 5 to 10 years? What is something that maybe you're excited about coming up on the space? And it's probably something we've already talked about, and maybe something that's concerning in the cyberspace that you see.
Well, I think, this will sound really weird to be excited about it, but I think what's going to happen is we're going to enter into an era where we're actually going to have regulations imposed on us that are going to make us do some of these things that we've just talked about. And I think, it's like everyone's like, why would you be excited about that? I'm like, well, because you know what? It's time for the OT space and like industrial control systems engineering to grow up and be like civil structural and say, civil structural, you pour a concrete slab, you erect a building. There's a lot of things that are imposed on you by code that you're like, this is never going to happen. I mean, have you ever opened up the International Building Code and you go, how come in Washington State I need to put hurricane straps? There's never going to be a hurricane here. I'm in Spokane, right?
Yeah.
But it's because you've created this lowest common denominator, you've created these fundamentals, and you want to have commonality, and it also makes the structure more resilient against other things, not just simply hurricanes. So I think we're going to get that, and I work in the mass transit space. We're seeing that come down through like TSA and DHS, and I think that's going to be a great thing, because then we're going to start to see people put these practices in place, because they're going to be held accountable to them. And it's not going to be anymore where you can just say, oh, well, we decided that was a scenario that would never occur here. And then that will impose a certain amount of discipline on code writers and on ICS engineers. And then I think we're going to get a better product across the board, as people move around and as they cross-pollinate. They'll bring their practices, and they're all kind of working to the same standard. And so I think that's gonna help solve this issue with the technical debt. What I am worried about is that we're going to see. I don't necessarily see that AI is going to make malicious actors more prevalent and more powerful, but I think what we're going to see is we're going to see the emphasis move to that. And so until we have a regulation that forces us to clean up our code and be disciplined, we're going to see organizations go out and spend money because they're going to get kind of scared into this idea that, well, now a malicious actor with AI, boy, they could really, you need to put in place, this new system that sits on another server that goes out and queries your systems and creates reports and gives you notifications of new patches and updates that you need to make. And it's like, wow, those are all valid, but we need to work at the foundation level, right? So we use that building metaphor again. It's like, we can make sure that the front gate is locked, we can make sure we've got intrusion detection, but you know what? If there's a portion of the foundation that's starting to collapse, they can probably get into the house that way, right?
Right.
So,
If I need a haircut and I got a bullet hole, I got shot, I'm probably I should prioritize getting that hole cut up and me stop bleeding before I go get my hair cut.
Right.
It's all about priorities. I need them both, but I need to do them in order.
right.
Or I may bleed out in the barber chair. Well, awesome, sir. So thank you for your time. Is there anything you want, call to action, people to know about, or anything about you before we go?
I'm a little bit of an odd duck when it comes to being in the OT realm. I kind of work with a lot of different organizations and find things there that they do that are really applicable to our space. And so one of them that I'm working with right now is INCOSE, that's the International Council on Systems Engineering. And usually you hear about that. That's the people that work in aerospace and defense industry. But they have a lot of practices. In fact, they work a lot with MITRE. They have a lot of practices that lead to really resilient system designs when it comes to failures. that are very applicable to the OT space when it comes to cybersecurity. And so coming up here in mid-September, September 14th, I'm going to be giving a tutorial demonstration on how to implement defensive coding in a Siemens PLC environment. So if people are in the Pacific Northwest, I encourage them to seek out the NCOSE Western States Regional Conference. It's going to take place at the Pacific Northwest National Laboratory in the Tri-Cities, where the Hanford Nuclear Reservation is. And it's going to be a great event, and we're going to be there, as I say, showing how to do these defensive techniques to protect your PLC environment at the foundational level.
Outstanding. We'll definitely put the link in the show notes so everybody can click on that and get all the details about that. Thank you again, Matt, today. I really enjoyed the conversation. I think it's a unique conversation that I don't hear a lot of folks having the conversation of, which is disappointing because it's super important that we look at those foundational items that are running our OT environments and to help us protect them. So thank you for your time. Thank you for your expertise. Keep fighting the good fight. I appreciate all you're doing, sir.
Thank you.
Thanks for listening to the Protect OT Cybersecurity Podcast. If you got some valuable information from today's show, please subscribe, rate, and review the show on Apple Podcasts, Spotify, or wherever you get your podcasts. To learn more about Aaron and to get your free copy of the OT Cybersecurity Solution Buyer's Guide, go to industrialdefender.com. That's industrialdefender.com, or you can click the link in the show notes.